Now that we have discussed frequency distributions and the different ways they can be presented, the next step is to discuss other important characteristics of distributions. In this class, we will consider the shape and height of distributions, how distributions can be divided into sections, and how raw scores can be transformed to standard scores. Here is an example of a positively skewed distribution. Notice that most individuals score at the lower end of the scale and that the tail stretches off to the right to capture people with higher scores. Tests with this type of distribution would be said to have a floor effect or do a poor job of discriminating between individuals at lower end of the distribution. Here is an example of a negatively skewed distribution. Notice that most individuals score at the upper end or receive highest scores on the scale, and that the tail stretches off to the left in order to capture the scores of individuals who scored lower on the scale. This sort of distribution would be said to have a ceiling effect or do a poor job of discriminating between individuals at the upper end of the distribution of scores. Before going to the next slide, see if you can answer this question. What is the shape of the distribution of income in the United States? The answer is that the income in the United States is positively skewed. Most individuals earn in the lower ranges of income, but the tail of the distribution stretches to the right to capture the scores of the few income earners who earn millions and millions and ultimately billions of dollars. Distributions also differ in height, which we call kurtosis. Distributions range from flat to peaked or tall. As a distribution becomes more peaked, there are fewer values in the tails of a distribution and more values in the center of the distribution. All things being equal, as a sample size increases, the kurtosis will become more peaked. Imagine a blanket on a floor and then picking up the blanket from the center. As the peak of the blanket or distribution becomes higher, the tails move in towards the center and the blanket or the distribution is not nearly as spread. Kurtosis is related to the variance of a distribution. The smaller the variance, the more peaked the distribution. Distributions are also often divided into sections in order to further understand a set of scores. Quartile divides a distribution into 4 equal divisions. It covers the range of scores that contain each 25% of the scorers. A decile divides a distribution into 10 equal divisions and covers the range of scores that contain each 10% of the scores. A percentile, finally, divides a distribution into 100 equal divisions, each containing 1% of the scores. Before going to the next slide, see if you can answer this question. What is the shape of a distribution of quartiles or percentiles? The answer is that the distribution has a flat shape. The distribution of quartiles or any other division of a distribution into equal portions would be flat because there'd be the same number of individuals at each segment or at each division of the distribution. Now let's turn our attention to transformations of scores. Raw scores on interval or ratio scales can be transformed to standard scores. In our discussion of the next few slides, we will need to refer to the mean and standard deviation of distributions. Please review these concepts as needed from the text or from the next class in this series to get more information about these concepts. A standard score expresses each score in a distribution in terms of how many standard deviation units they fall above or below the mean of the distribution. Transforming a score to a standard score allows us to compare the results of tests on many different tests by transforming them all to the same scale of measure. In psychology, we're interested primarily in 5 different types of standard scores. In z-score transformations, scores are changed such that the mean of the distribution is equal to 0 and the standard deviation is equal to 1. Thus, a z-score of 1.5 corresponds to a raw score that is 1.5 standard deviation units above the mean. And a z-score of negative 0.75 is 0.75 standard deviation units below the mean. A z-score is obtained by the formula you see in the slide. The mean of the distribution is subtracted from a score in the distribution and then divided by the standard deviation. For example, if we had a distribution in which the mean was 30 and the standard deviation was 4, a score of 35 would be transformed to a z-score by subtracting 30 from 35 and dividing by 4, which would equal 1.25. We would then describe the score of 35 as being 1.25 standard deviation units above the mean. In a t-score transformation, scores are changed such that the mean is 50 and the standard deviation is 10. Thus, a t-score of 60 is 1 standard deviation unit above the mean. This can be computed by using the z formula that we just used above. If we subtract 50 from 60 and divide by 10, we receive a score of 1. Many personality tests such as use t-scores, the most important of which are the scales of the MMPI and the MCMI. Before going to the next slide, see if you can determine the z-score associated with a t-score of 35. The answer is negative 1.5, or 1.5 standard deviation units below the mean. The answer was obtained by subtracting the score of 35 from the mean, 50, and dividing by 10. To continue our discussion of the important types of standard scores we use in psychology, we turn next to IQ score transformations. When using an IQ score transformation, raw scores are changed such that the mean of the new distribution is 100 and the standard deviation is 15. Thus, a score of 112 is 0.80 standard deviation units above the mean. We can determine this by using the z formula. We subtract 100 from 112 and divide by 15, which equals 0.80. Many achievement tests, memory, and intelligence tests use IQ standard scores, the most important of which is the Wechsler Adult Intelligence Scale series and the Wechsler Intelligence Scale for Children series. The Wechsler Intelligence tests also use another important standard score transformation for its subtests. Using this transformation, scores are changed such that the mean of the new distribution is 10 and the standard deviation is 3. Thus, a score of 13 is one standard deviation unit above the mean. We can determine this by using the Z formula. We subtract 10 from 13 and divide by 3, which equals 1.00. A standard score is also used in academic achievement tests and transforms scores there such that the mean of the new distribution is 500 and the standard deviation is 100. Using the z-score formula, we can verify that a score of 450 is 0.5 standard deviation units below the mean. We subtract 500 from 450 and divide by 100, which results in a score of negative 0.50. Tests such as the SAT use this standard score transformation strategy. We will be using these scores frequently during a discussion of test results, especially for normed reference tests. You'll need to memorize these types of standard scores and the tests mentioned above that use them. Before going on to the next slide, see if you can express a full-scale IQ score of 90 in terms of z-scores or standard deviation. The answer is negative 0.67 or 0.67 standard deviation units below the mean. The answer was obtained by subtracting the mean from 90 and dividing by 15. In the next series of slides, we will use visual information to help describe what happens when scores are transformed using a standard score transformation strategy. In this slide, we have a symmetrical distribution of raw scores with a mean of 30 and a standard deviation of 4. Thus, the scores of 34 and 26 fall one standard deviation unit above and below the mean respectively. Now let's see what happens to this frequency distribution when we use standard score transformations to transform these scores. In this slide, the raw scores have been transformed from the original scale and have been transformed into z-scores. Here the mean of the distribution, which used to be 30, is now 0, and the standard deviation, which used to be 4, is 1. Thus the score of 26 was converted to a z-score of negative 1 by subtracting 26 from 30 and dividing by 4. In this distribution, the raw scores from the original distribution have been transformed into t-scores. Note that the mean of the distribution is now 50 and the standard deviation is 10. A score of 60 in this distribution corresponds to a score of 34 in the original distribution of raw scores. In this slide, the raw scores from the original distribution have been transformed into IQ scores. Note that the mean is now 100 and the standard deviation is 15. A score of 85 corresponds to a score of 26 in the original distribution. Both are one standard deviation unit below the mean. In this slide, the raw scores from the original distribution have been transformed into the standard score transformation used in the subscales of the Wechsler test series. Note that the mean of the distribution is 10 and the standard deviation is 3. A score of 16 on this scale corresponds to a score of 38 in the original distribution, as both of them are 2 standard deviation units above the mean. In this final slide, the raw scores from the original distribution have been transformed into standard scores used by academic achievement test. Note that the mean is 500 and the standard deviation is 100. A score of 300 corresponds to a score of 22 in the original distribution, both of which are 2 standard deviation units below the mean.